The wooden track layout. Reverse merge. Wooden tracks, electric trains. By Gary Schick. November 2025. In this episode of our series, Wooden Tracks, Electric Trains, we look at merge track components. We will demonstrate how merge tracks allow us to create interesting circuits, such as the reversing loop. We will also demonstrate the concept of a bypass constructed to allow a train to avoid entering a switch that may be in use by another train. In the video clip, we are watching two train engines travel in a layout that relies heavily on merge track components. The video segments examine how merge tracks operate in combination with other track components. At the end of this episode, we expect that you will say how obvious it all is. But without the necessary insights, it is not quite so obvious. If while watching this video clip you completely understand the layout and its routes, then perhaps you do not need to continue watching. But if you have any question as to what is unusual or unexpected in this video clip, then you should pay attention to what we will show you next. In layouts presented in our videos on YouTube, we use a section of wooden track that we refer to as merge track. Unfortunately, most people do not refer to this track section using the name merge. When we search for switch track, we find components we call merge. In our applications, the component shown in the left of this photo is most accurately called a merge, and it is not a switch as some may say or think. When we search for a mechanical switch, we find a component we refer to as a switch, as shown in the photo on the right. In our opinion, a switch and a merge are nearly opposites. A merge is combining track, and a switch is a separating or diverting track. A merge causes a train to travel a predetermined route. A switch allows us to decide between two route choices. In the photo, notice the blue control handle extending above the switch. The handle is pulled or pushed to change the switch setting and hence alter the direction of travel. The switch handle is attached to a throw bar that actuates a critical movable element in the switch. The critical movable element that guides train wheels to either straight or diverting tracks is called a blade or a point blade. The specific model of the switch component shown in the photo situates the handle along the switch curve, but other switch models situate the handle along the straight edge. A merge track does not have or need a handle, throw bar, or blade, and there is no moving element. In a merge track section, there are two entrances. The two entrance paths leave the entrances within the track section and eventually combine as they approach the single exit. One of the entrance paths curves towards the exit, while the other entrance path is a straight line to the exit. A train travels through a merge track in the paths inherent to the design of the component. A train generally enters a merge track at one of the two entrances, but it is also possible and useful for a train to enter the merge track at the exit. Entering a merge track at the exit is called a reverse merge, and the usefulness of a reverse merge will be the principal topic of this presentation. Three-way merge tracks with three entrances are also available components, but we are not going to discuss those here. A switch track has a single entrance and two exits. At a switch, two possible paths are available, and a choice of path is made or changed at almost any time. The path selection is made by pointing the blade at the desired exit. One of the exit paths curves away from the entrance, while the other exit path is located along a straight line from the entrance. At a switch, a train usually enters at the single entrance and leaves at one of the two available exits. The exit taken by the train depends on how the switch is set, which is to say, where the blade is pointed. It is also possible to enter a switch from either of the two exits. A switch entered at the exit operates somewhat like a merge. However, the switch will need to be set to point to the specific exit to ensure proper travel across the blade. In other words, the blade should point to the exit which is being used as an entrance before a train enters at the exit of a switch. Finally, both switch and merge tracks are available with pegs at either the entrance or the exit location, and the sockets are always at the other location or locations. For the remainder of this episode, we will focus on how the merge track is used in our layouts. To illustrate the utility of merge track, we first look at some reversing loop layouts we created for a demonstration. In several previous videos found in our YouTube series, we described a circuit or loop category called a reversing loop. A design for a small reversing loop circuit is shown here. We previously described the reversing loops in our YouTube videos and showed animations and video clips with trains traveling in reversing loops in our layouts. However, we will review these reversing loops once again because there are details which we did not address. All reversing loops have a central section of track where a train will travel first in one direction and then in the opposite direction. To complete a reversing loop, the central bidirectional section is traveled in the two opposite directions, regardless of where the train starts in the circuit. A reversal of direction is achieved at each of two return paths located at both sides of the bidirectional section. Each of these two return path areas begins and ends at a merge track section. Each return path makes two connections to the merge track, one connection at the straight entrance and the other connection at the curve entrance. So, a train located in a return path area will exit the return area after traveling the merge. When leaving either of the return areas, the train travels into a merge entrance and travels out of the merge exit. When leaving the return path, the train is traveling in the opposite direction from when the train entered that return path. Because there are two return path areas, one on each side of the bidirectional central section, the train will reverse direction in the path either side of the bidirectional track. So, reversal of direction is completed when the train passes through either of the two of the reciprocal merge tracks and re-enters the bidirectional section. A train in the bidirectional area can only leave this area by entering a merge exit, either the exit for the left side merge or the exit for the right side merge. When a merge track is entered at the merge exit, the path through the merge section is called a reverse merge. So, a reverse merge occurs when a train passes from the bidirectional area into a merge track at the merge exit and enters the unidirectional return path at one of two merge entrances. While we have stated that travel into the exit of a merge section is a legitimate and permitted use of a merge track, the reverse merge behavior requires further explanation. Over the course of several video clips we will now show, we will see why understanding the path of a reverse merge can be tricky. In this video clip, we started the red engine in the central bidirectional section, traveling towards the return path on the right. Please notice the train path as it enters the merge track on the right, then exits the merge track along the straight exit from the merge section along the bottom part of the return loop. The return path on the right side causes the train to travel a counterclockwise semi-loop. This is not a complete loop because the train is traveling in the opposite direction at the completion of the semi-loop. The train then enters the merge track at the curved exit, which is situated in the upper part of the merge section in this video. In this reversing loop construction, the train will always travel the right side return path in the counterclockwise direction. This travel path is caused by the mechanics and physics of the train wheel alignment in the merge track section. Leaving the right side return path, the train travels on the bidirectional track section once again, but in the opposite direction from when the video clip started. As a result, the train arrives at the left side merge track exit and exits the left side straight entrance of the merge section, located along the bottom of the left side return path. On the left side, the train travels in a clockwise direction until it reaches the left side curved exit merge, situated in the upper part of the merge track. In this reversing loop construction, the train will always travel the left side return path in the clockwise direction. Once again, we see the mechanics and physics of the train wheel alignment causing a specific exit to be taken in the merge track section. After passing through the merge section, the train exits the merge track at the merge entrance, now traveling in the same direction as at the start of the video clip. It is important to notice that not only does the train complete the circuit, but there is a consistent travel path resulting from consistent behavior traveling across the merge track. We will next look at a different reversing loop where the travel path is not what you might expect. The layout shown in this photo is almost the same as the previous layout, but we made a small change in the bidirectional track section. In the bidirectional section, we added a curved track at the right end, causing the position of the right side merge track and the right side return path to be positioned downward, as we see in this photo. We emphasize that the two return paths in this layout are the same as before. However, the bidirectional section is different, with the addition of a curved section on the right before the merge. Also note that the inside arc of the curve added is on the opposite side of the track from the inside arc in the curve exit of the neighboring merge track. The arc in the added track and the arc in the merge track are both sections of circles with the same radial length. However, the center of the circle of the added curve is not on the same side of the track as the center of the circle of the merge track, and that makes the curves inverse. The addition of the inverse curve in the bidirectional area at a location adjacent to the merge track is an essential change in the track configuration. In what way might the change alter the travel of the train, other than lengthening the distance of the bidirectional travel area? In the next video clip, watch very carefully as the train travels through the merge track after leaving the newly added curve in the bidirectional section. When the train passed through the right side merge, what happened? If you missed the difference, you will be able to get a second look in a few moments. On the left side, the train travel is the same as before, and the train travels the return loop in the clockwise direction and returns to the bidirectional area. Now traveling in the original direction, the train enters the bidirectional area. However, after again passing the new curve on the right side of the bidirectional area, we see a new behavior at the merge track. Instead of taking the straight path to the entrance at the bottom of the merge, the train takes the curve towards the entrance at the top of the merge track. The exit taken causes the train to travel the right side return path in the clockwise direction. When a train exits from a curved track and enters the exit of a merge track with the inside arc of the merge entrance centered on the opposite side from the first curve, the train wheels are shifted within the track so that the train travels across the merge into the opposing curve. As a result, the curve entrance in the merge becomes the exit instead of the straight entrance. If there is no curve in the path just ahead of the merge track, the train exits from the merge track at the straight entrance. Without the preceding inverse curve ahead of the merge track, the train travels counterclockwise in the right side return path. The addition of the inverse curve changed the path of the train as it passes through the merge track. Adding the inverse curve ahead of a merge track caused the train to travel clockwise in the right side return path. We will show the two video clips simultaneously. The video clip with a straight bidirectional section and the video clip with the inverse curve before the merge. This will provide a clear comparison of the train behaviors in these layout variations. In this split dual display, we show video clips with a train traveling on similar track layouts. Both layouts contain reversing loops with a bidirectional track section in the center. Both layouts have a train engine that travels into the exit of a merge section to make a reverse merge, as the engine leaves a bidirectional area. In the layout on the left side of the display, in the right side return path, the train travels in a counterclockwise direction through the return path. In the layout on the right side of the display, the train on the right side return path travels in a clockwise direction through the return path. The difference between the two layouts is an inverse curve found only in the layout displayed on the right. The inverse curve section preceding the merge track causes a change in direction across the nearby merge track, and the curve entrance in the nearby merge is used as an exit instead of the straight entrance being used as the exit. The original layout on the left part of the display lacks a curve section in the bidirectional area. Lacking the inverse curve before the reverse merge, the train uses the straight entrance to exit from the reverse merge. In the video clip displayed on the right side of the bidirectional area, an inverse curve before the nearby reverse merge changed the travel direction in the right return path from counterclockwise to clockwise. For this video clip, we installed a continuous curve section before the merge at both the right side return path and the left side return path, so we have a symmetric layout. The curve track that precedes the merge exit forms a continuous arc with the arc in the neighboring merge track. With this circular curve configuration, the adjacent merge curve and the preceding curve have the same circle center. The changes made were in the bidirectional area, so both return paths remain unchanged from layouts previously shown. When we watch this video clip, we notice that the direction of travel in the return paths begins along at the straight merge track entrance and ends at the curve merge entrance. Since the same reverse merge behavior occurs at both the right and the left return paths, we see the engine travel counterclockwise in the right return path and a clockwise in the left return path. In other words, we see the same path traveled in this layout as when we had straight track adjacent to the merge. The reverse merge behavior, when entering the merge exit from a continuous curve, is the same reverse merge behavior as when entering the exit from straight track. However, the reverse merge behavior when entering the merge exit from a continuous curve is different from a reverse merge behavior when entering the exit from an inverse curve. Was it a surprise to see a curve before a reverse merge that does not change the position of the wheels in a way that alters the direction of travel in the merge? To make sure we fully understand the reverse merge, we built several similar configurations. In every configuration we built, we confirmed that only an inverse curve impacts the direction of travel in the reverse merge, and consequently in the direction traveled in the subsequent return path. Here, in part 1 of this episode, we analyze forward and reverse merge behaviors in the context of a reversing loop route. This analysis provides a foundation for other applications of the merge track. In part 2, we will look at more complex layouts, where we utilize merge tracks to create other types of loop routes and to resolve issues in our layout designs. We will end part 1 with a challenge question. Where will a train entering the curve at the top left travel, with a merge configuration comprised of 2 merge tracks that are oriented as shown in this photo? For the answer to this question, please watch the next video in this episode on the Wooden Tracks Electric Train channel on YouTube. The Wooden Track Layout Reverse Merge, Part 2, Inverse Merge Crossing. The information presented in this video is an honest representation of an actual wooden track layout using battery-operated toy trains. These videos are intended for entertainment and the enjoyment of hobbyists and enthusiasts. The train layout design and construction are our own and are provided without financial incentive. We share these videos on YouTube for own satisfaction. We welcome constructive and polite feedback.